This is carbon.
That's what I suppose it is.
This is carbon.
Let's try it.
Okay, let's change the environment. What's already doing was depositing the layers, but I'm going to remove those layers from the morning. So my title is Atomic Layer Etching for Pitch Splitting, Nanofabrication, and Damage-Free Process. So yeah, who we are? We are AlixLabs, sitting in Lund, Skåne, near to Malmö, just across the bridge. We are almost 20 people, 10 permanently working in the labs, and we are sharing Nano Lund, Mayfib, and plus Pro Nano Labs in the Lund. And rest 10 people are partially hourly working with us, some computational physics, and some other people are sitting around. So outlines, I'm going to discuss about the atomic layer etching. And then how during that atomic layer etching processing, we split the pattern. This is our trademark, ALE pitch splitting, and then we have this process is damage-free process, even smoothening the surface of the material. So then we have some results and summary. So let's start with atomic layer etching. It's a slow process, but it's cyclic, and it's a self-limiting process. And how it approach, like first you need to modify the layers with some etchant gas, and then you need to remove it. And this is just after modification the layer to lower the binding energy from the beneath, and then we have an energy supply in the correct range. That's etch that layers. And advantage of this atomic layer is low surface damage and plus precise control of etch depth. So this is the canard published in 2018. Actually, this is the ion distributions according to the etch per cycle. So he described 3 windows over here. In the first window is incomplete etching, incomplete removal of the layer, that 0 to 20 electron volt. And then we have a window 2 starts from the 20 to almost 85. So that's the ALE window. It's a self-limiting and layer by layer removal per cycle. So and then we have another third window that's maximum like RI, sputtered, a lot of other physical smuttering parameters happening over there. So these 3 windows describes during this processing. This is the one cycle. So we are describing on this ALE window. It's called plateau regime, like plateau area of the ALE. So how this is a schematic diagram. In the first, actually this is a cyclic process. The cycle consists of the 4 steps. In the first step, to modify the layers with the external gases. Let's say in silicon case, we have a chlorine, just to modification of the layers. And the first half cycle, and then second step is purge to remove the extra gases from the chamber. And then we have a third step, activation or etching in the third step, and to remove the products from that step. And then we have a purge 4 to remove all the products from the chamber. So physically chemisorption in the first half cycle, and then we have an ion irradiation to chemically sputter the surface. So actually there's a kind of 2 ALE. It's a quasi ALE or real ALE. If we are talking about the real ALE, then we have to more precise. Mostly we are doing like quasi, but still in the ALE, real ALE, ideal ALE, we need to consider these parameters. It's a synergy. I forgot to put the mathematical formula over here. The synergy, it's a both etch and feed, and the surface radiations are essential to achieve. If one of the step is removed or omitted, then there's no etching, or there's no other ALE regime over there. But another second step is etch rate is totally independent of the number of cycles. I mean, each cycle have a same number of same etch depth. Third, of course, other parameters we are considering in the ideal case of ALE, minimum damage for exposed surface smoothing even. saturation effects, and we have an activation energy. The ALE window is achieved on this plateau regime, as we showed in the before curve. There's a plateau curve. It's a ALE window. Second window was the ALE. So that was the real ALE. Let's have some animations of this ALE. So we have, in this case, chlorine gases comes up to modify the surface and then rest in the second step. This is the one cycle. First is just to modify the surface, and then second step to just remove those extra gases from the chamber. And then we have a modified one layer, top layer, and the surface, the binding energy between this and then there is a difference to remove. That's the lower the binding energy by after this modifications. And then we are easily radiation the surface to remove these products from this. This is argon layer, argon radicals. So this is how the one surface, one layer is removed by this ALE process. So what is our trademark is APS. APS means ALE based pitch splitting. ALE pitch splitting. So how does it work? I'm not gonna tell you the real story behind this, but it's just how it happens. Like how the edges of this pattern is behave like a mask, and then we are just splitting the structures like this. So this is the animation for pitch splitting and APS purpose for AlixLabs. So experimental setup. Mostly we used for this ALE purpose SOI samples, and we have two kind of tools over here in the Nano Lab and then Pro Nano AlixLabs. We have ICP-RA system, plasma thermotachy, and then we have a Plasma Lab 100 ICP-RA. It's Oxford systems. And then ALE processes were performed at different RF regime, like from 7 watts to 25 watts. And process pressure was of 3 millitorr. And we have two kind of ALE, molecular ALE and atomic ALE. In the atomic ALE, we have ICP all the way is on. And in the molecular, there is no ICP. We use the molecules to modify the surface. So the results. So these are the first results what the AlixLab is stand for. So first, one left side is the half of the nanowires is covered with some mask and half is exposed. So you see those exposed part is split, but those not exposed part is not split. So that's the APS. That's the pitch splitting was done by AlixLabs. So this is the TEM. Image of the fin-like silicon structures, silicon nanowires, and then we have a APS processing, and then we just clearly see that. We're splitting the nanowires in. So another part is we just smoothening the surface. How this is the AFM characterization. First is the reference sample, and then we have some molecular ALE, quasi ALE kind of, and then we have atomic ALE. So in both cases, we just the roughness is removed, and then we just smoothen the surface by RMSE value 0.02, and then we have 0.04 in both cases. But compared to the reference one, so summary, optimized quasi-ALE in standard ICP-RA tool with improved surface quality of the material. And then we have a APS breakthrough technology based on atomic level processing. So this is APS process technology, alternative to self-aligned multi-patterning, reduce process complexity and therefore cost efficient, energy savings, lowering the environmental impact, improve throughputs, and relying on already existing equipment what we have. Thank you very much.